Hello my beautiful students, so welcome back to a new video of Deeksha Karnataka channel. So this video is dedicated to the PU1 champions because for you people your examination is knocking the door, right? So I already have posted one marker sure shot video and now it's time to go for the 2 to 5 marker sure shot questions. So yes, without further delay, let's get started. So here you can see first question that comes from the first chapter, that is define empirical formula. So as you know, this is the answer that is also given out there. You will get everything in the PDF version if you need. So you can see empirical formula is the simplest formula which represent the simplest whole number ratio of the various atom present in a compound. That's it. So now molecular formula, that is also an important question for the 2 marker. So here you can see the definition is given also. Now you can see this question is one of the most relevant question from this type of chapter. So yes, we will do the numerical problems from this chapter as well. So yes, let's proceed with the numerical. So first you can see a compound contain 4.07% hydrogen, 24.47% carbon and 71.67% chlorine. So its molecular mass is given is 98.96 gram per mole. What are its empirical and molecular formula? So this will be a 3 marker question for you. So let's try it. So to apply for this type of question, first let's just make a simple table. Like let me just write here. I'm writing the element. Just beside that I will make the column for the percentage composition. Next I will make the column for the atomic mass. Next, percentage composition plus atomic mass divided by atomic mass, divided by atomic mass. Next, we will try to find out the simplest ratio. So we can write dividing by smallest values. And here we can write out rounding off value. Okay, so now let's put one by one. So first we will proceed with the carbon. So for carbon, percentage amount is how much it is given? 24.47, right? 24.47%, right? Atomic mass of carbon, we know. What I have to do here? Percentage composition divided by atomic mass. So 24.47 divided by 12 you have to do. Okay, so almost it will come up to be 2.02, right? This particular thing we will proceed later. Let's proceed the same thing with the hydrogen. Hydrogen I'm having 4.07%. Atomic mass is we know 1. So here also we will get 4.07, right? Now for the chlorine. So for the chlorine you will get 71.65% and we know the mass is 35.65 and percentage composition, that's gonna be 71.65 divided by 35.65. Okay, it will give you almost something like 2.01. So you can check the simplest value is coming 2.01, right? So here what I'm going to do, 2.02 divided by the smallest value, that is 2.01. Here I am going to do, so this is almost, it will come as 1 if you do round off. Here 4.07 divided by 2.01. Here 2.01 divided by 2.01. This is just to make the ratio simple. So here if you do, it will come almost like 2. Here also 1. So round off also 1, 2, 1. So this is the scenario. This is the rounding off value, like that you can calculate. So from here I can write down the empirical formula. So let me write it here. So empirical formula, it's coming something like carbon is 1, right? And as you can see, hydrogen is 2. So CH2 and Cl, right? Now what I have to do, I have to calculate the N value. So N is basically molecular mass of the compound divided by the empirical mass. So molecular mass, you can see it's already given 98.96. Now if you just calculate the molecular weight of this particular compound, it will come up to be 49.50. 49.5. So just simply divide it, 49.50. Okay, and you will almost get it to be 1.99, or you can write it as 2. So now in order to find out the molecular formula, you just have to multiply, or just empirical formula whole n, that is the formula for the molecular formula. Okay, so what I am going to do, CH2Cl whole twice, right? Because n value is 2. So overall the thing will come as C2H4Cl2. So that is my answer. So I guess it's clear to you. This type of one problem you can expect in your examination, and this is the most relevant problem. Maybe the same problem you can get in your examination, because this is directly taken from the NCERT. So yes, without further delay, let's proceed for the next problem. So another important question, that is, what is limiting reagent? So as you know, the limiting reagent, like that limits the reaction because they gets consumed fast, right? So for this case you can give one example as well. Nitrogen, hydrogen will give you ammonia if you are taking lesser amount of hydrogen or lesser amount of nitrogen. Then because of the nitrogen being a limiting reagent, the reaction will be stopped even though hydrogen is excess. Like that you can give one example. Okay, so let's proceed with the next question. Here you can see this is related to the limiting reagent itself. N2 and H2 reacts with each other to produce ammonia according to the equation. Okay, so calculate the mass of ammonia produced if 2.0 into 10 power 3 gram of N2 reacts with 1 into 10 power 3 gram of H2. Reacts with 1 into 10 power 3 gram of H2. Fine. So let's proceed one by one. So first what we will do is, we will just convert everything to number of moles. So let's do that thing at first. So from the equation we can get, see, 1 mole of nitrogen is reacting with 3 mole of H2, right, to give you 2 mole of ammonia, right? So 1 mole of nitrogen means it's 28 gram, 3 mole means it's 3 into 2, that is 6 gram, and ammonia is 17 gram, to 2 into 17, that is 34 gram of ammonia. It is in general. Looking at the equation I can tell you just by calculating with the stoichiometry. Okay, so now what I will do is, I will just convert the given mass with molecular weight. I will convert it to number of moles. So you can see number of moles of N2 at first calculate, that is, you can see 2 into 10 cube, right, means 2000 divided by 28. So that's going to be how much? 71.43. Okay, and now I'm going to calculate the same for the hydrogen. So hydrogen is given 1000 divided by 2, that will give you something like 500. Okay, so now how I have to proceed? So we have to find out the limiting reagent at first. So what they are saying, by looking at the equation you can tell that 1 mole of N2 always will react with 3 mole of hydrogen, right? Hence, if I am having 71.43 mole of nitrogen, then it will definitely react with 74.43 into 3, that is 214.29 mole of hydrogen, right? But given is 500 mole, so definitely this going to be the excess, right? If this is the excess, then nitrogen is limiting. So why I am at finding out the limiting at first? Because with respect to limiting reagent only I will get the amount of product. Okay, so now you can see how to proceed further. So we have to calculate the amount of ammonia, right? So from 1 mole of N2 I am getting how much ammonia? I am getting 2 mole of ammonia, 2 mole of NH3, right? So I am having how many moles? 71.43, right? 71.43 mole of nitrogen. Hence I will get the ammonia, that is 2 into 71.43 mole of ammonia, that's going to be 142.86 mole of ammonia. Okay, so now it is the number of moles, so you have to just simply calculate it to gram. How to calculate? 142.86 into molecular weight of ammonia, that is 17. So that will give you something like 2428.62 gram of ammonia. Okay, so I guess it's clear. First part is clear to you. Now you can see question number 2. If you see that, will any of the two reactant remain unreacted? Yes, hydrogen will remain unreacted. Why? Because this is given excess. Okay, so now let's see how much amount will be unreacted. Okay, so here you can see N2 is limiting, H2 is excess, right? So how much hydrogen is used? You can see 70. Let me just proceed with a basic thing. 1 mole of nitrogen will use 3 mole of hydrogen, right? From here I can tell that 71.43 mole of nitrogen will use 3 into 71.43 mole of hydrogen, so that is nothing but 214.29, right? So now from that particular case, if you just convert this thing into mass, so you will get it this into 2, because molecular weight of hydrogen is something 2. Okay, so from here I will get it something like 428.58 gram. Okay, 428.58 gram. Then how I should find out what is the leftover? So leftover amount, mass of H2 that is left. So this much amount 428.58, this will react. So mass that will left, that is something like 1000 minus 428.58, that will give you something like 571.42. So this much amount of hydrogen will be left out. So this is the answer of question 3. Okay, I guess this is clear to you. Let's proceed further. Just for this type of problem, step by step try to analyze. At first find the limiting reagent, find out excess reagent. With respect to limiting reagent only, calculate the amount of product. Okay, so yes, let's proceed for the next question. Okay, here one more problem you can see. Very important problem. Okay, so the density of 3 molar solution of NaCl is 1.25 gram per ml. Calculate the molarity of the solution. Okay, so first let's calculate the molar mass. From the basic we will start. A lot of things we have to do here. See, molar mass of NaCl is for sodium it is 23 and for chlorine it is 35.5. So I can write molecular weight of NaCl is basically 58.5 gram per mole. Fine. So now definitely we will calculate the mass of the solute. Okay, so mass of NaCl, because they are saying that 3 molar solution. 3 molar solution means 3 moles of that particular solute is present. By definition it is proven. So 3 into 58.5 gram, that is 175.5 gram. Right? Now we are having density. So D equals to m by V we know. Okay, so from here what I can do, I can calculate the mass. Okay, so from here I can write mass equals to D into V, right? So from here mass equals to density is given 1.25. Let the volume be 1 liter, because 3 molar solution means 3 moles present in 1 liter, right? So we can take it 1000 ml. So mass is coming as mass of the solution. Definitely it is of the solution. Okay, mass of the solution will come up to be how much? 1250 gram. Right? So from here I can calculate mass of solvent as well. So mass of solvent, we know mass of solution is 1250, mass of solute is 175.5. So if you subtract, you will get the mass of solvent, that is 1074.5. Now simply calculate the molarity actually. Okay, so if you calculate the molarity, so simply just put the formula, that is a mass of solute. If I write, let's say W2 by M2 into W1 into 1000. Okay, let me just put it here. So from here if I just put mass of the solute is how much? 175.5, that we already calculated, into 1000 divided by, we are having molecular weight, right? That is 58.5 into mass of solvent, that is 1074.5. So if you calculate the entire thing, it will come up to be 2.79 molar. Okay, that is the answer. I guess you understood this. Let's proceed for the next question. Okay, so before going to the next question, one thing I just wanted to tell, that as you know, your seniors are the best mentor for you people, right? So suggest your seniors to proceed with the ABHYAS KCET test series given by Deeksha Karnataka, because if they can get a good opportunity in some good colleges and some top 1000 rank in Karnataka, then they will guide you to get top 1000 rank in Karnataka in KCET examination as well. So yes, if you are having seniors who are preparing for their KCET examination, please recommend this thing to them. Okay, so just a small message to you people. Let's proceed. Okay, so here comes the question from the second chapter, that is atomic structure. Give the two drawbacks of the Rutherford atomic model. So I don't have to tell you, we already know it. So it doesn't suggest any specific radius, and like emission and absorption spectra could not be explained utilizing this. Next, you can see explain the particle nature of electromagnetic radiation by Planck's quantum theory. So here comes the entire explanation about the Planck's quantum theory. So in accordance to the Planck's quantum theory, what we know, that the body that emits and radiate all type of radiation, right? So that is called black body radiation. So these particular phenomenon, or these particular property is shown by the particle nature of the substance only, right? And like for the black body radiation, if you just proceed with an exact frequency distribution of the emitted radiation, then it depends upon the temperature, right? So the intensity will be increased if you give more temperature. Okay, you can see the wavelength versus intensity graph is also given out there. So like that, you can just proceed with the particle nature. Okay, I guess it's clear to you. Let's proceed. Here you can see what is photoelectric effect. This type of question you can expect out of it. So simply you can just write down like the process of emission of electron from the surface of the metal when they are exposed to the certain amount of frequency of light, that is called photon. Okay, so that is called photoelectric light. So you are having a surface, on that particular, let's say I'm having this type of metal surface. On that surface, if photon is striking, then the free electron above the surface, they will come out. Okay, that is a photoelectric effect. Okay, so I guess it's clear. Let's proceed. Okay, here comes a problem. Okay, a 100-watt bulb emits monochromatic light of wavelength 400 nanometer. Calculate the number of photon emitted per second by the bulb. Okay, so power is given, that is 100 watt. Power is given, that is 100 watt. 100 watt is similar to that of the 100 joule per second. Okay, now you can see you have to calculate the photon emitted per second. So energy of the photon you can calculate out of it. You know the formula of energy. Energy equals to hc by lambda, right? So put the value here. H value, H is the Planck's constant, that is 6.626 into 10 power minus 34. Into c is the speed of light, that is 3 into 10 power 8, divided by lambda is how much? 400 nanometer, right? So let's convert it to meter. So 400 into 10 power minus 9. So if you calculate the entire thing, it will come up to be something like 4.969 into 10 power minus 19 joule, right? Now the number, right? So the number of photons that is emitted by 100 watt bulb, that you can write 100 divided by 4.969 into 10 power minus 19, sorry. Okay, so if you calculate this, it will come up to be something like 2.012 into 10 power 20 second inverse. That's it. This is your answer. I guess this is clear to you. Yes, let's proceed for the next question. Okay, so this is a question from photoelectric effect, right? Yes. So let's proceed. The threshold frequency, that is nu 0 for a metal, is 7 into 10 power 14 second inverse. Calculate the kinetic energy of an electron emitted when radiation of frequency is given that hits the metal. Okay, fine. So we know direct formula we can apply out there. We know kinetic energy is basically equals to h nu minus h nu 0, right? So from here, just let's simplify nu minus nu 0. Okay, now let's put the value out there. 6.626 into 10 power minus 34 into okay, nu 0 value is given 7 into 10 power 14, and the radiation frequency 1 into 10 power 15. Okay, so here you can see we can proceed like 10 into 10 power 1.0 into 10 power 15 minus 7 into 10 power 14. Like that we can do. Then for a simplification we can just convert the 10 power, the power of 10, like in the same way, so that we can take common. Okay, let me do it. 14. Okay, from here what I can do is 1.0. Okay, so here what I can do is I can take 14, 10 power 14 common. Okay, so if I take 10 power 14 common, it should be 10 now. So 10 minus 7, right? Okay, so now if you just calculate the entire thing, it will be something like 6.626 into 10 power minus 34 into 10 power 14 into 3. So if you calculate the entire thing, it will come up something like 1.988 into 10 power minus 19 joule. Okay, so that's gonna be your answer. I guess this is clear to you. Yes, let's proceed. Okay, so now here I can see give the 3 limitations of Bohr's theory. So here are so many limitations, all the limitation I kept here. You can just pick any 3 out there. So first you can see it is only applicable for one electron system. It couldn't explain the Zeeman effect and Stark effect, like quantization of the angular momentum idea was like it was not practical based. Okay, and it was only a theoretical based thing. Okay, now here you can see in the postulate of Bohr theory that electron revolve in well-defined orbits around the nucleus with well-defined velocities. It is not acceptable if you proceed with the Heisenberg's uncertainty principle. So like this you can just take any 3 point out of it and you can proceed with the answer. Let's see, here you can see the next question. That is what is the frequency and wavelength of a photon emitted during the transition of n equals to 5 state to n equals to 2 state in the hydrogen atom? We can proceed with the Rydberg's equation actually. So yes, let's proceed. Okay, so nu equals to, we know, delta E by h, means h equals to E equals to h nu. From here I can write it. So from that particular thing I can write delta E equals to the Rydberg's equation, right? RH into 1 by n1 minus 1 by n1 square by 1 by n2 square, right? So let's proceed. Let's put the values here. Rydberg's equation value is, Rydberg's constant value is 2.18 into 10 power minus 8. Sorry. 10 power minus 18 into 1 by n1 is 2 square minus 1 by 5 square. So I'm not going to the detailed calculation. So if you calculate it, you will get something 4.578 into 10 power minus 19 joule, right? So now if you just see nu equals to delta E by H, again I'm coming back to this equation, just put the value of delta E, that is 4.578 into 10 power minus 19 divided by H is the Planck's constant, that is 6.626 into 10 power minus 34. So if you calculate this, your nu will come up to be 6.91 into 10 power 14 Hz. Okay, so I have calculated the frequency. Now I have to calculate the wavelength. Okay, so we know the formula of wavelength is something like lambda equals to c by nu. So c is basically the speed of light, that is 3 into 10 power 8 divided by nu is, just now we calculated 6.91 into 10 power 14. Okay, this is 14, this is not 4, this is 14, 10 power 14. Okay, so if you just calculate this, it will come up to be, I'm not going to a detailed calculation, you can do it, you will get it something like 434 into 10 power minus 9 meter. Okay, so if you can convert it to nanometers, so it will be 434 nanometer. Okay, this is in the term of wavelength and this is in the term of frequency. I guess this is clear to you. Yeah, let's proceed further. So here you can see, give the postulates of the Bohr's theory of atomic model. So postulates of Bohr theory, there are so many postulates, you can just pick up any 3 out there, most important 3. Okay, so they are definitely mention about the stationary orbit and definitely mention about the angular momentum, that is mvr equals to nh by 2 pi, means let's say this particular point is very much important. Okay, and you can see electron will neither gain or nor accept any energy when they will rotate in a particular orbit, but when they will jump from the lower energy state to higher energy state, they can just accept the energy. So these are the points, and here energy released and absorbed by the electron just equals to the energy gap in between 2 successive orbitals. Okay, these points you can mention out there. Okay, so let's proceed. Calculate the wave number. Calculate the wave number for the longest wave transition or wavelength transition in the Balmer series of atomic hydrogen. Okay, so longest wavelength we will get when the transition is the shortest. Okay, and shortest wavelength we will get when the transition is longest. Always remember that. So for this case, the shortest transition we have to check. Balmer series means n equals to 2, right? From 2, n equals to 2, they will jump, electron will jump. So what is the shortest jump? From 2 to 3, that is the shortest jump. So that I will take. So yes, let's proceed with the formula. Rydberg's equation equals to RH into 1 by n1 square minus 1 by n2 square. Overall it will come up to be centimeter inverse, because you can see it is nu bar. Nu bar means 1 by nu. So yeah, let's put the value of Rydberg's constant, that is 109,677, okay, into 1 by n1 square, that is 1 by 2 square minus 1 by 3 square. Okay, so if you just calculate, I'm just not going for the detailed calculation, it will come up to be 15233 centimeter. So that is the wave number. Okay, so yes, That is the answer. So if you just want to convert it to meters, so it will be something like 1.5233 into 10 power 6 meter inverse. Okay, so that is your answer. I guess it's clear to you. Let's proceed. So write the de Broglie's wave equation. So whenever you are writing any kind of equation, make sure you are writing the abbreviation. So that is nothing but lambda equals to h by p, or you can write lambda equals to h by mv. So what is lambda? Lambda is the wavelength. Okay, what is h? H is the Planck's constant. Okay, and p is basically the momentum. Okay, so here in terms of p, again further you just break down with respect to m and v. Then m is nothing but the mass of electron and v is the velocity of electron. Okay, so this is your de Broglie's wave equation. I guess it's clear to you. Let's proceed. Calculate the mass of photon with wavelength 3.6 Armstrong. Okay, so it's basically very easy one. We can use a de Broglie's equation and we can just proceed with it. So here you can see, lambda is given as 3.6 Armstrong, right? So we can convert it to meter. So from Armstrong to meter conversion, we can do it 3.6 into 10 power minus 10 meter. Right? So now velocity, if you just take, okay, now if you just put it in the equation, that is lambda equals to h by mv. Mass you have to calculate, right? Mass of electron, mass of photon, let's write photon. You have to calculate, so h by lambda into v. So h is 6.626 into 10 power minus 34. Okay, so yes, divided by, okay, lambda will come up to be, okay, mass, if I write mass of electron, that is 9.1 into 10 power minus 31 kg. Okay, into, here you can see you have to put the velocity, right? Velocity of electron in the first orbit, it comes up to be something like 2.19 into 10 power 6 meter per second. Okay, so now if you just calculate the entire thing, I'm not having the answer correctly, so if you just calculate the entire thing, you will get the mass of the photon. Okay, just you can put the things in the calculator and you can just calculate the value. I guess it's clear to you. Let's proceed. State the Heisenberg's uncertainty principle, give its mathematical expression. It's a very important question. So as you know, it's impossible to determine simultaneously both the position and the momentum, okay, of a moving particle like electron. Okay, and if you just look for the expression, that is delta x into delta p, p is the momentum, right, is greater than equals to h by 4 pi. That's it. Okay, let's proceed. Okay, this type of numerical, it is from the Heisenberg's uncertainty principle. A golf ball has a mass of 40 gram and a speed of 45 meter per second. If the speed can be measured within the accuracy 2%, calculate the uncertainty in position. Okay, so mass is given. Mass is given, that is 40 gram. So mass I can write, yes, 40 gram. I will take it into kg. It means 0.040 kg, right? So now what I have to do, what I am having, speed, velocity. Velocity is something 45 meter per second. That's it. Okay. Now what they're saying, let's say velocity prime. Okay. They're saying that speed can be measured within 2% accuracy. So 2%. So 2% means it should be something like v equals to 2% of 45 meter per second. Okay, so if you calculate this, it will come up to be something like 0.9 meter per second. Okay, now let's put all the things into the equation. That is delta x into m into delta v equals to h by 4 pi. Okay, so let's put everything over there. Uncertainty in position means delta x you have to calculate. So h means 6.626 into 10 power minus 34 divided by 4 into pi value is 3.14 into, okay, velocity is 45 meter per second. I can write it as, mass is 0.040 kg. So I can write it as 4 into 10 power minus 2, right? Into accuracy in velocity, if you consider, it will come up with 0.9 meter per second, right? So if you calculate the entire thing, it will come up something like 1.46 into 10 power minus 3 meter. So that is your answer. Okay, I guess it's clear to you. Let's proceed further. Here you can see, explain the significance of quantum numbers. So first you can see principal quantum number, that is n. So definitely it defines the shell, the size of the orbital, and also the energy. And if you just look for the next one, that is azimuthal quantum number, that is L. This particular thing is also called as the subsidiary quantum number, and it majorly defines about the shape of the orbital. Okay, next if you proceed, see, if you are having the L value like 0, 1, 2, 3, 4, then it will indicate the different subshell. Like if you are having 0, then it is S, if 1, then it is P, if 2, then D, if 3, then F, like that. Okay, next you can see magnetic quantum number, it gives the spatial orientation. Okay, and next if you proceed with the spin quantum number, it will give the direction of spin, if it is clockwise or anti-clockwise. It can have two value, plus of and minus of. It will, if it is plus of clockwise, minus of anti-clockwise, like that. I guess it's clear. Let's proceed. How many radial nodes are present for the 4D orbital, right? So yes, so let's do it. If I am having 4D orbital, it means angular node value. If you want to write angular node value, I am having two type of node, right? Angular node and radial node. Angular node can be represented as only L, and radial node can be represented by the formula n minus L minus 1. Okay, so I am having 4D orbital. 4D means n equals to 4. Okay, L equals to how much? L equals to 2, right? So angular node is going to be 2, and radial is going to be 4 minus 2 minus 1, that is 1. So total number of nodes, if you find, that is 2 plus 1, that is 3. Okay, I guess it's clear to you. Yes, let's proceed. Give the difference between orbit and orbital. So this is the difference. You can see orbit means a circular path around the nucleus where the electron revolves, but orbital means a region or a space, okay, where the probability of finding electron is maximum. Okay, now an orbit, actually it represents the energy level, includes the sub energy levels as well, but orbital, whenever it comes to, it's actually comprises a sub energy of a main energy level. Okay, so orbits are circular, but orbital has different shape, like dumbbell shape for the p orbital, like that. Okay, so like that you can just take any 2 or 3 differences and you can just proceed. Aufbau principle, very important. You can see it states that the electrons enter into different atomic different atomic radius with respect to their increasing order of their energy. Okay, so definitely in n plus L rule, definitely we will proceed with the same thing. Okay, so here you can see explain n plus L rule. This question also you can expect. So according to this particular rule, what basically happens, with one which is having higher value of n plus L, they are having more energy. Okay, if n plus L value are same, then if n value is high, then it is having more energy. Okay, so this is the diagram in which you can explain that what is the order of the energy in which the electron gets filled up. Okay, from here only 1s, 2s, 2p, 3s, 3p, this particular energy order comes. Next you can see here some examples are given. You can just go through it. I guess you will understand for n plus L rule. Okay, so let's proceed. Pauli's exclusion principle. So Pauli's exclusion principle means no two electrons can have same set of 4 quantum number. Okay, even all the 3 are same last spin quantum number, they must be different. Okay, so like that. Next, Hund's rule of multiplicity. All the 3, Aufbau principle, Pauli's exclusion principle and Hund's rule, all the 3 are important. Don't skip any one of them. So what is Hund's rule is suggesting? So electrons pairing, it's related to the pairing. Electrons pairing and in p, d and f orbital cannot occur until all the orbitals of a given subshell contains at least one electron each. Okay, one electron will be given to the orbital and then the pairing will take place. Okay, so here you can see this is a correct order. It's showing here 1s, 2s, 2p, but here you can see one wrong order is also showing here. You can see 1s, 2s, 2p, like that. Okay, so yeah, let's proceed further. Okay, so let's proceed with the next question. Here you can see the Vivid Bharati station of All India Radio Delhi broadcasts on a frequency of 1368 kHz. Calculate the wavelength of the electromagnetic radiation emitted by the transmitter. Which part of the electromagnetic spectrum does it belong to? Okay, so let's proceed with the formula. Okay, so we can take nu equals to c by lambda. So that will work here. So further we will just put the value. Nu is given as 1368 kilohertz. So let's convert it to hertz, means 10 power 3 second inverse, equals to C is 3 into 10 power 8 meter per second. Okay, lambda we have to calculate. We will calculate it in meter. Okay, so if you from this equation, if you calculate lambda, it will come up something like 0.0219 into 10 power 5 meter. Okay, so from here you can just convert it. From here I can tell that 219 meter it will come up. So from here this is the answer. I guess you understood. Just apply the nu equals to c by lambda. From there you just can calculate lambda in meter. Okay, I guess this is clear to you. Yes, let's proceed. The wavelength range of the visible spectrum extends from violet to red. Express this wavelength in frequency. Okay, so again same formula we can use. Nu equals to c by lambda. Okay, so here 3 into 10 power 8 meter per second divided by, they are saying that extends from violet means 400 nanometer, right? So 400 into 10 power minus 9 meter. Okay, so if you calculate this, it will come up to be something like 7.50 into 10 power 14 hertz. Okay, now frequency of light. frequency of light, if you want to calculate, it will be something like nu equals to c by lambda, that is equals to 3 into 10 power 8 divided by, here red is 750, right? 750 into 10 power minus 9. So this is my meter per second. This is also meter. So from here what I will get, he will get almost like 4 into 10 power 14 hertz, right? So I guess you understood the range of the frequency, that is 7, not 7, it's 4.0 into 10 power 14 hertz to 7.5 into 10 power 14 hertz. Okay, this is in terms of frequency. So I guess it's clear, just nothing. Lambda is given, with respect to that you have to find the frequency, that is the range of it. Okay, next here comes the next chapter, that is the periodic table. So modern periodic law, you can see the physical and chemical properties of the element, they are the periodic functions of their atomic number. Okay, next IUPAC. So we know there are different names for 1, 2, 3, 4, 5, 6 for the element after 100, right? So with respect to that, 1 represent un, 2 represent bi, 0 represent nil. So un being nilium, that's it. Okay, next, what are isoelectronic species? So the species, they are having same number of electron, they are called isoelectronic species. Okay, so you can see some examples are given: O2 minus, F minus, Na plus and Mg2 plus. They are all of them are having 10 electrons each. Okay, next, define the ionization enthalpy. Very important question is this. How does it vary along the period and down the period in the periodic table? So basically it is the amount of energy that is required to remove one electron from the outermost orbital of an isolated gaseous atom in its ground state. Okay, and it increases along the period and decreases along the group. Okay, the reason is also that you can just go through. The first ionization enthalpy of boron is less than that of beryllium. The reason is something, you can just write down the electronic configuration and you will get to know about it. So for boron it is 2p1, right, the valential electronic configuration. So in case it is 2p1, it's very easy to remove one electron right, but in case if it is 2s2 for beryllium, it's full filled s orbital, right? So that's the reason it's really difficult to remove one electron whenever it's very stable. Okay, yeah, let's proceed. The first ionization enthalpy of nitrogen is more than that of oxygen. Again, just write down the electronic configuration, the things will be clear to you. Nitrogen, it is having the half filled p orbital, right, 2p3, right, that is having some extra stability. But whenever it comes to the matter of oxygen, it is 2p4 system, right? So for oxygen, it's easier to remove one electron than that of the nitrogen. Let's proceed. Define electron gain enthalpy. How does it vary along the period and like down the group? Let's see. So electron gain enthalpy is the amount of energy that is released during the addition of an electron. Means from the outside, from the infinite distance, you want to put one electron to the valence orbital of an atom. So the amount of energy that is released, it is called the electron gain enthalpy. Okay, so like this increases along the period because of the effective nuclear charge increases and decreases down the group. Okay, so the reason is also there, I guess you will understand. Let's proceed further. Here you can see the electron gain enthalpy of oxygen or fluorine is less negative than that of the succeeding elements, sulfur or chlorine. Explain. Okay, so why? Because whenever the electron is getting added in oxygen and fluorine, in that particular case it is getting added in N2, right, two shell, right? As a result of this, 2 shell is up to 2p, right? There is no d orbital, so it faces a lot of repulsion, inter-electronic repulsion. But in case of sulfur and chlorine, whenever it is added in 3p, right? So 3p means it is having by default vacant 3d orbital. So whenever it is having by default 3d orbital, so this repulsion is much less, right? So that's the reason for oxygen and fluorine the value is less negative. Okay, let's proceed. Here you can see which of the following will have most negative electron gain enthalpy and which one is the least negative. So here you can see, I guess this one type we did it in the MCQ as well. So most negative electron gain enthalpy, that is the chlorine, and less negative is because it's phosphorus. Okay, so formal charge on oxygen, it's complete calculation is there in the NCERT. Please proceed with the calculation. It's very important. There is a formula. Utilizing that formula, you can calculate the individual formal charge of individual oxygen of the ozone. Okay, so this is the calculation you can see. Let's proceed. Okay, give the limitation of the octet rules. So whenever it comes to the matter of octet rules, there comes several limitation. Okay, so let me just tell you, for few cases, maybe outermost orbital is containing more than 8 electron, but still they are stable. Like PF5, SF6, this type of system, they are containing 10 electron, 12 electron, but they are stable. So they are not following the octet rule, right? Next, you can see there can be lesser than that of octet, but still they are stable, like lithium chloride, BH2, LCl3, this type of thing. Okay, so now odd electron species like NO, NO2, okay, they also do not satisfy the octet rule. Now these are the things you can just take. You can just take any 3 of them or 2 of them, any, like on the basis of the marks that is given to you, and you can write it down. Okay, let's proceed. Resonating structure for CO3 2-. So here you can see it can exist in 3 resonating structures. So I guess you know how to draw it, and here also it's shown. I guess it's clear to you. Let's proceed. Dipole moment of BF3 is 0. The reason is basically if you just see, BF3 is a trigonal planar structure, right? So once the structure is trigonal planar, as you can see, just a minute. So the dipole moment direction is like that, like that, like that. So for these two, the resultant dipole moment comes like this. Okay, so now these two can cancel out and it can become 0. Okay, so as a result of this, you can say that the dipole moment of BF3, it comes up to be 0. Next, you can see what is dipole moment, what is the unit. It is basically the product of charge and the distance. Okay, a distance between the positive and the negative charge, and it can be represented with respect to dBi. Okay, and coulomb meter also. Okay, let's proceed. The resultant dipole moment of NH3 is greater than that of NH3. So here comes the reason. Just look at the diagram. So here for the NH3, if you see, here comes a dipole moment because of the presence of the lone pair, right? But for NF3, definitely above also because of the lone pair 1 dipole moment, but below nitrogen and fluorine dipole moment, fluorine is more electronegative, so resultant dipole moment will pass through this. So above 1, below 1, they can cancel out to some extent. Okay, as a result of this. But here in case of NH3, there is no, dipole moment that is cancelling out this one, right? So as a result of this, you can say NH3 is having greater dipole moment with respect to NF3. Okay, give the main postulates of the VSEP. It's a very important question, 3-marker question it comes. Okay, so here a few things you can just take, like 2 or 3 points, major important points you can take. So it depends upon the valence shell electron pairs. The electron pairs, they repel each other. Okay, the repulsion is how the lone pair repulsion is maximum, then lone pair, then bond pair. Okay, so lone pair is concentrated around the central atom, and bond pair is pulled out between 2 bonded atoms. So any 3 you can just pick and you can just proceed. I guess it's clear. Let's proceed. Okay, so here comes predict the shapes of BaCl2, BF3, CH4, NH3 and H2 molecules on the basis of VAC theory. So beryllium chloride, you can see it's a linear molecule. Okay, this is the structure already given out there. BF3 molecule is something like trigonal planar. This is my BF3 molecule, that is trigonal planar. Okay, now if you just look at the ammonia, ammonia is basically trigonal, pyramidal structure with 3 bond pair and 1 lone pair. Okay, so this is the structure overall, and the bond angle becomes not exact tetrahedral bond angle because of the lone pair bond pair and bond pair repulsion. Okay, the angle reduces to 107.5 degree. Okay, next, water shape, if you ask, then it is basically again trigonal pyramidal, you can call it. Okay, so pyramidal structure where the lone pair repulsion and lone pair bond pair repulsions are also there, that makes the angle in between hydrogen oxygen reduces to 104.5 degree. Okay, so that is one of the important point. Okay, so water is shorted. Next, okay, next question, give the difference between sigma and pi bonds. It's very important. Okay, for the last question, the bond angle between hydrogen and hydrogen oxygen for water. Okay, this thing you have to remember, and sometimes they ask the reason behind it. Okay, the reason is very simple: lone pair repulsion followed by lone pair bond pair repulsion. That makes the bond angle reduced. Okay, let's proceed. Here comes the next question, sigma and pi bond difference. You can just pick any 2 or 3 points in accordance to the marks. Usually they give this question in 2 marker. So yes, any 2 or 3 you can pick. I guess it's all good. Let's proceed. Explain the sp hybridization in acetylene molecule. So here you can see the overall discussion is done. So sp molecule, sp hybridization means one s and one p orbital, they are taking part in the hybridization pattern, and rest p orbital, let's say one s and let's say px is taking part in the hybridization. So py and pz, okay, they will be free. So then py and pz, they make the pi overlap to give you 2 consecutive pi bonds. So one sigma bond you will get because of the sp overlap, and another 2 pi orbital you will get because of the py and pz overlap. That's it. Okay, I guess it's clear. Let's proceed. sp3d2 hybridization in the formation of SF6 molecule. Okay, so basically what happens in this case, one unpairing of electron takes place. So usually sulfur ground state configuration, if you just see 3s2 3p4, right, 3s2 3p4. So here what happens, unpairing of electron. So 6 unpaired electron we need to accommodate 6 fluorine, right? So we need 2 unpaired electron. So from 3s and 3p, one electron they get unpaired and they send those electron to 3d. Okay, so initially it was something like this. So 3s I had 2 electron, 3p I had like this. Okay, so from 3s and 3p, these 2 paired up electron, they get unpaired and they send the electron to the 3d orbital so that they can accommodate the 6f orbital. Okay, now 6 unpaired electron, they will make the hybridization sp3d2 and they will accommodate 6 fluorine atom. I guess it's clear. Yeah, this is how the sp3d2 looks like. Okay, you don't have to be bothered about the structure, just remember how they form the hybridization. Okay, so I guess it's clear to you. Let's proceed further. Okay, what is the type of hybridization of the carbon atoms marked with the star? So first case carbon is basically sp2. Next, if you just see, this is sp3 carbon, and third one is sp. Okay, so you can just calculate this thing with respect to steric number. Steric number means the number of sigma bond plus the number of lone pair. Carbon has no lone pair, just count the sigma bond. Okay, yeah, let's proceed. How many types of bonding and anti-bonding molecular orbitals are formed in diatomic molecules? So we have two options. One is bonding, another one is anti-bonding. We can get sigma and pi bonding molecular orbital and sigma star and pi star anti-bonding. That's it. Okay, explain the non-existent helium molecule based on the MOT. So here you can see, if you just look at the just hypothetically think that He2 molecule exists, and if you make the MO diagram out there, then you can see 1s and 1s, total 4 electron, and if you find out the bond order, non-bonding bonding minus anti-bonding, 2 minus 2, so bond order comes 0. So if bond order can 0, definitely there no bond exists in between two helium. So as a result of this, you can say He2 does not exist. Okay, so let's proceed with the next question. Explain the formation of oxygen molecule on the basis of MOT theory. So let me just draw the MO for oxygen. So normal electronic configuration, I guess you know, 1s2, 2s2, 2p4. Just let me show you the MO diagram for oxygen. So this is my energy axis. Okay, so here I will draw first one oxygen, and here my another oxygen. This is my 1s. Okay, this is also my 1s. Okay, this is my atomic orbital of oxygen. This is also my atomic orbital of oxygen. Okay, in the middle we will draw molecular orbital of O2. So 1s and 1s, they will combine to give you one bonding and one anti-bonding. So this is my sigma 1s bonding, and this is my sigma star 1s anti-bonding, right? So similarly, if you proceed with the next one, okay, let me show you the molecular orbital diagram for oxygen. So first we will draw the energy axis. So below here we will start with the 1s of one oxygen atom. So this is my atomic orbital of oxygen. Here also another 1s. This is also atomic orbital of oxygen. Okay. Now in the middle we will draw molecular orbital of O2, right? So 1s will combine to give you one bonding, and it will give you one anti-bonding like this. Okay, so this is called sigma 1s and this is called sigma star 1s. Okay, now I am having 2s, here one 2s and here one 2s. Okay, so this is my 2s will give you again one bonding, and it will give you one anti-bonding. Okay, so that is my sigma star 2s. Okay, the anti-bonding is named as sigma star. Okay, now I am having p orbital. P orbitals are 3, so let it be 2px, 2py, 2pz. Here also, let's say I am having these 3, 2px, 2py and 2pz. Okay, let's say px is the molecular axis, so it will make a sigma at first. Let's say 2px is making the sigma, so sigma 2px, and it will make 2 pi orbital with 2py and 2pz. So I will name it as pi 2py and pi 2pz. Okay, above also, now it's time to draw the anti-bonding. So anti-bonding I will do with the same sigma at first, that is sigma star 2px, and then we will do the pi, that is pi star 2py and pi star 2pz. That's it. So this is the overall MO diagram. Okay, so now just let me just clean this thing a little. So this is my entire thing. Now we will just fill up the electron in this. Okay, so 1s is having 2 electron, 2s 2 electron, and 2p 1 2 3 4. Okay, now same thing we will do here. 1 2 3 4 5 6 7 8. Okay, so total 1s and 1s, total 4 electron we have to accommodate here. 1 2 3 4. Here also 1 2 3 4. Here I am having total 8 electron next case. So 1 2 3 4 5 6 7 8. You can see these 2 electron, they are unpaired. Okay, they are unpaired. So I am having pi star, or like in the pi star py and pz, this is my homo orbital, that is highest occupied molecular orbital. Here I am having unpaired electron, and hence I can call them paramagnetic. O2 is paramagnetic in nature. Okay, so this is how you should represent. I guess it's clear. This is the complete diagram for the MO, and you can just write down the electronic configuration on the basis of this. Okay, so here sigma 1s2, sigma star 1s2, like that. You can see here it is written the number of electron thus occupied. Okay, the same thing I drawn over there. I guess it's clear now. Let's proceed further. Okay, explain the hydrogen bonding with example. We can have two type of hydrogen bonding, intramolecular and intermolecular. Okay, so intermolecular, you can see it is in between two different molecule. Okay, like H2 and H2O, the oxygen and hydrogen of two different H2 atom, I mean two different H2O molecule, they can have the bonding, that is intermolecular, right? And intramolecular means within the same molecule you can have the hydrogen bonding, that is intramolecular. What is adiabatic process? Okay, here we are entering into the thermodynamics. Okay, so let's proceed. So adiabatic process, I guess you know, there is no exchange of heat. Okay, so like there will be no exchange of heat with the surrounding to the system. Let's proceed. State the first law. It's very important for your board examination. First law, I guess you know, the energy of the isolated system is always constant, or you can write the energy can neither be created or cannot be destroyed, or it can only be transformed from one form to other form. So the mathematical formula also you need to write, that is del U equals to Q plus W. Here also, please, whenever you are writing the mathematical formula, please mention what is U, what is Q, what is W. Okay, abbreviation is mandatory. Next, you can see what is free expansion and what is the work done during the expansion of an ideal gas, both in reversible and irreversible case, both the cases I will tell. Expansion, free expansion means whenever it is happening, there is no external pressure against it. Okay, whenever the expansion is happening in a vacuum. Okay, and the work done is taken as 0. Okay, for both reversible and irreversible cases for an ideal gas. Okay, let's proceed. Here comes one numerical problem. Okay, let's proceed with the problem. A gas absorbs 120 joule of heat and expands again external pressure of 1.10 atmosphere from a volume of 0.5 liter to 2.0 liter. What is the change in internal energy? Okay, let's proceed. We will proceed with the first law of thermodynamics. Okay. Okay, so we know delta U equals to Q plus W. So Q value is given is how much? Plus 120 joule because heat is absorbed. So from here W we know minus P external V2 minus V1, right? So let's put the value here. Minus P external is minus 1.10 atmosphere, and what is the change? V2 is 2 liter, 2.0 minus 2.0 minus 5 liter, right? 0.5. Okay, so now if you just calculate this thing, it will come up to be how much? Minus 1.65 liter atmosphere. Okay, so liter atmosphere. So now if you just want to convert it to joule, you have to multiply this thing with the 101.3. Okay, let me just convert it. Minus 1.65 into 101.3, that will give me the joule unit from the liter atmosphere. That will be something 167.145 joule. Okay, now I can put this thing in this particular equation. So delta U becomes plus 120 plus 120 because Q value plus what is the W? Minus 167.145 joule. Okay, this will give you something minus 47.135 joule. So that's going to be your answer. Okay, I guess it's clear to you. Let's proceed further. Okay, calculate the total work done when 1 mole of a gas expands isothermally and reversibly from an initial volume of 20 decimeter cube to a final volume of 40 decimeter cube at 298 Kelvin. Okay, fine. So for this case, we will calculate definitely using the formula W equals to minus 2.303 nRT log V2 by V1. Very important formula. Okay, so here let's put the things. Minus 2.303, R value is, okay, N here is 1 mole, right? So 1, R value is 8.314. Okay, temperature is 298 Kelvin. Okay, log V2 is 40 divided by V1 is 20. Got it? Now if you just calculate this entire thing, it will come up to be something like 1717.46 joule per mole. This is the thing. Okay, I guess this is a direct question actually. Reversible work done formula, you can just simply apply it and then just put the value out there, you will get the answer. I guess that's clear to you. Yeah, let's proceed further. Okay, one more numerical. So here you can see the question. The reaction of cyanide with oxygen was determined in a bomb calorimeter, and the delta U was found to be minus 742.7 kilojoule per mole of cyanide at this temperature. Calculate the enthalpy change for the reaction. Okay, whenever they will just give the formula bomb calorimeter, just calculate the del N value at first. Okay, one formula only you have to apply whenever they will give the bomb calorimeter this type of problem. Delta H equals to delta U plus delta NG RT. This is the only formula you have to apply whenever they are mentioning about the bomb calorimeter. Okay, so let's at first find out delta NG. So that is product minus reactant, right? So product is how much? See, I will just take nitrogen and carbon dioxide because H2 is liquid. I'm not gonna take because Ng, delta Ng means change in like a number of moles of product or reactant. It's only the gaseous we have to take. So 2 minus, again you can see ammonium cyanide, that is also solid, we are not going to take it. So 2 minus 3 by 2, right? That will give you something 0.5. Okay, so yes, now let's put everything in that equation, in this equation. Okay, so delta H is going to be, so what is the U value? Minus 742.7 kilojoule plus 0.5 into 8.314 into 10 power minus 3. Why I am doing it? Because U is given in kilojoule. That's why here also with R I am multiplying this with 10 power minus 3. Okay, and temperature is given as 298 Kelvin. Fine. So if you calculate the overall thing, then it will come up to be something like 741.741 minus 741.46 kilojoule per mole. Okay, so that is the answer. Okay, so I guess you understood this. This is the enthalpy change for this reaction. So whenever they will mention about the bomb calorimeter, you can use this formula, delta H equals to del U plus PV. PV means del Ng RT. That's it. So del N you calculate and put everything over there, you will get the answer. Okay, let's proceed. Okay, one more numerical. Yes, let's see. Calculate the standard change in internal energy at 300 Kelvin for the reaction this, when standard enthalpies of formation of CCl4H2O CO2 are given and HCl. Okay, fine. So for this case, how we should proceed with the problem? See, enthalpy of the reaction can be calculated by enthalpy like change in product, enthalpy of product minus enthalpy of the reactant. Okay, so here in this reaction CCl4 to H2O CO2 HCl, from here also we are going to apply the same thing to get the enthalpy of the reaction at first. Let's do it. So enthalpy of the reaction, if you calculate, that is the sum up of the This is the sum up of the enthalpy of the product minus sum up of the enthalpy of the reactant. So what you have to do now, just put the value. Okay, so products are carbon dioxide and HCl. Okay, let's put directly minus 394 plus 4 times of HCl, right? 4 into minus 93. No need to change the unit, keep it in kilojoule, that will work. Minus, now let's put the reactants. Reactants for the CCl4, that is minus 107 plus 2 into minus 242. So once you just put the value, then calculate, it will come up to be something like 175 kilojoule per mole. Kilojoule per mole. Got it? Now what you have to do, again that formula that I already told you, I'm just doing it here. Delta H equals to delta U plus delta Ng RT. Okay, so now here delta U actually you have to find out. So the equation becomes delta H minus delta Ng RT. Okay, delta H value I can put from here minus 175 kilojoule per mole minus, okay, delta Ng value we have to find out. So delta Ng is basically equals to how many product? 4 plus 1, both of them are gaseous. So 5 minus 2, that is 3. Okay, so 3 into 8.314, so kilojoule, right? So 10 power minus 3 into temperature is given as how much? 300 Kelvin. Okay, so if you calculate this thing, it will come up to be something like minus 182.5 kilojoule per mole. Okay, that is the answer. I guess this is clear to you. Yes, let's proceed further. Okay, derive the relation between Cp and Cv. So that's a very important question actually. Cp minus Cv equals to R, that you have to prove. Okay, so from where we should start? We know Q equals to C into delta T, right? Now Q at constant volume and Q at constant P. So whenever Q at constant volume, it will be Cv del T. Okay, and that is nothing but delta U, right? And whenever it comes to the P, it is Cp del T, that is nothing but delta H, right? Now for ideal gas, what we know? Delta H equals to delta U plus delta RT. 1 mole of ideal gas I am taking definitely. So let's put the value here. For delta H I am putting Cp delta T, and for delta U I am putting Cv delta T. Okay, that is equals to plus R into delta T. Okay, so now if you just take the delta T common out there, delta T will be cancelled out and Cp minus Cv, it will come up to be R. Yes, so it is derived. I guess it's clear. Yeah, let's proceed further. Define enthalpy of the reaction. Illustrate with an example. So here you can see the change in enthalpy when all the moles of reactants as indicated in the balanced chemical reaction have completely reacted to form the product. So enthalpy of product minus reactant. So one example is also given out there. So yes, let's proceed. Here comes enthalpy of fusion. So there are several options: enthalpy of combustion, enthalpy of fusion. So I suggest all of them you should remember the definition at least. Okay, so like I have mentioned here few of them, I guess. Here you can see the enthalpy that change accompanies by melting of 1 mole of solid. Okay, that is a fusion. So for the ice, it is given value. Enthalpy of atomization is a very important question. The enthalpy change accompanying the dissociation of 1 mole of given substance, definitely in the gaseous state. Okay, that is the atomization. Let's proceed. Here comes one numerical problem. Let's proceed with it. Okay, calculate the enthalpy of combustion of liquid benzene. Okay, given that value of enthalpy of formation of benzene CO2 and H2O are this. Okay, let's proceed. So at first write the equations. So I am having benzene. I have to combust the benzene, right? That is C6H6 plus O2. That will give you CO2 plus H2. What do you have to do? This enthalpy you have to find out, right? So first balance it. So if I do it as 6, here if I make it 3, and here I can make it 15/2. Okay, now you can see it's a balanced one. So by the given information, I can come back to this equation. So what are the equation that is given? Enthalpy of formation of benzene, carbon dioxide and water. Okay, let's form the benzene at first. First equation is something like 6 carbon plus, definitely 6 carbon will make the benzene, plus H2 will create C6H6. So hydrogen must be 3, right? For this case, enthalpy is given as plus 48.51 kilojoule. Okay, next equation they are saying that carbon dioxide I can make by C plus O2 will give you CO2. The enthalpy is given as minus 393.5 kilojoule. Next they are giving water. So H2 plus, I can write half O2, okay, will give you H2O. So enthalpy value is given as minus 285.83. So utilizing these 3 equations, I have to come up with the first equation, that is a benzene. Okay, the combustion of benzene. So what I can do is equation 2, this is my equation 1, let it be, this is my equation 2, this is equation 3. Okay, let me do it here. So I can do equation 2 into 6 I can do. Just a minute. Equation 2 into 6 plus equation 3 into 3. Plus I can reverse equation 1. Okay, then I add them. So equation 2 into 6. So 6 carbon plus 6 O2 will give you 6 CO2, right? Along with that enthalpy value also you have to multiply with 6, right? So enthalpy will come up to be 6 into that one, 6 into minus 393, it will come up to be minus 2361. Okay, just let me just make a border. Okay, next equation is 3 into equation 3. Sorry. So 3H2 plus 3/2 O2 will give you 3H2 in the liquid. Okay, here also enthalpy you have to multiply with 3. So enthalpy will come up to be something 3 into 285.83. So it will come up to be something like minus 857.49. Okay, next you can see reverse of equation 1. Okay, So C6H6 will give you 6 carbon plus 3H2. Okay, if you are doing the backward reaction, then enthalpy value will come up to be negative, right? So minus 48.51. Okay, so now if you just see everything after cancelling out, 6 carbon will be cancelled out, 3H2 will be cancelled out. So you will come up with the first equation, that is C6H6 plus 15 by 2O2 will give you 6 CO2 plus 3H2. Yes, and the enthalpy also if you add, that is minus 2361 minus 857.49 minus 48.51, then you will end up with minus 3267 kilojoule per mole. Yes, that is the answer. Okay, so I guess you understood this. At first derive the equation and then proceed so that you can get the main equation and then add or subtract the enthalpy value in accordance to that. Okay, so let's proceed with the next question. Here you can see, derive the relation between Kp and Kc. So the relation itself is very much important for the numerical purpose. So let's do it. So we will take a general equation at first. Let's say small a plus small b of b, it will give you small c of c plus small d of capital D. So if you want to write the Kc for this, it will be something like Kc equals to concentration of C power C, concentration of D power D, divided by concentration of A power A, concentration of B power small b, like that. Okay, so now if you follow the ideal gas equation, from there we know PV equals to nRT, right? So PV equals to nRT. From here I can write P equals to N by VRT. From here I can write P equals to CRT, because N by V means C. So now from here P equals to CRT, with that perspective I can find out PA, PB, let's write here PC and PD. Okay, so now let's proceed with PA at first. So that's definitely gonna be concentration of A into RT. For B, definitely it's going to be concentration of B into RT. For this case, it's going to be concentration of C into RT. This is going to be concentration of D into RT. Okay, so now if I just write the Kp form, you can see Kp can be written in the form of partial pressure of C power C, partial pressure of D power D, divided by partial pressure of A power A into partial pressure of B power B. Now here let's put the value from the last few equations. So partial pressure of C, we can write concentration of C into RT whole power C, right? Whole power C. Partial pressure of D also in the same way, we can write concentration of D into RT whole power D, divided by, here also same thing, we can write partial pressure of A into RT whole power A. Here also we can do partial pressure of B into RT whole power B. Okay, so now in the similar way, what I can simplify it, you can see C power C D power D divided by A power A into B power B, and RT we can write it in this way, RT power C plus D minus A plus B. This whole thing we can write as delta N. So this particular thing is nothing but Kc, right? So I can write Kc into RT power delta N. So what is delta N? Delta N is basically the difference between the stoichiometry of the product minus the reactant. Always remember, this should be gaseous product and gaseous reactant only. So this is the relation between Kp and Kc. I guess you understood this. Let's proceed further. Okay, so here comes one problem that is related to the same thing, I guess. I mean that particular relation itself. So here you can see for the equilibrium 2NoCl gives 2No plus Cl2. The value of equilibrium constant is given. Find out the Kp. Okay, so from the relation itself we can calculate. So here you can see first we will calculate the del Ng value. So del Ng, whenever I am going to calculate, that's going to be, we will calculate only the gaseous reactant. So 2No, so 2 plus 1 Cl2, right? This is the product side, minus reactant side is also 2, so I am getting 1. Okay, now Kp equals to Kc into RT power delta Ng, right? So let's put the value here. Kc is given something like 3.75 into 10 power minus 6. R value we know 0.08314 into 1069 is the temperature. Power delta N means 1, right? Now what I can do, I can calculate and your Kp will come almost something like 0.000333. This is the answer. Okay, I guess this is clear to you. Yeah, let's proceed next. Okay, one more numerical problem we are having here. So here you can see for the following equilibrium, Kc is given at 1000 Kelvin. NO plus O3 gives NO2 plus O2. Fine. Both forward and reverse reaction equilibrium are elementary bimolecular reaction. What is the Kc for the reverse reaction? Okay, Kc, whenever we are finding out for the reverse reaction, then what we have to do, we just have to take the reciprocal. So whenever I am taking the Kc, let's say I am taking the Kc prime. Okay, Kc prime is the constant for the reversible reaction, I mean reverse reaction. Okay, that will be 1 by Kc. Okay, so simply just calculate 1 by 6.3 into 10 power 14. Okay, that will give you the answer. That is something like 1.59 into 10 power minus 50. That's it. I guess you understood this. Let's proceed further. Okay, so here one more numerical problem you can see. 1 mole of H2O and 1 mole of CO are taken in 10 liter vessel and heated to 725 Kelvin. At equilibrium, 40% of water reacts with CO according to the equation this. Okay, calculate the equilibrium constant. Fine. So first write down the reaction. That is our first rule. Okay. H2O, this is gaseous, plus CO, that is also gaseous, hydrogen gaseous, plus CO2 gaseous. All of them are gaseous. Fine. Let's initial concentration build. Initial H2O, initial mole, let it be 1. Okay, here also let it be 1. There definitely it is 0. 0 means when the reaction has not started. At equilibrium. At equilibrium definitely some x amount of this and x amount of this will be produced. So here it will be 1 minus x and here it will be 1 minus x. Okay, so now concentration of H2O, how I should find out? So concentration of H2. So that must be 1 we started with and 40% of water reacted, right? So 40% means 40 by 100, okay, divided by 10. Okay, so now mole per liter. Okay, so now because 10 liter vessel they told, right? So from here if you calculate the concentration of H2O, it will come something like 0.04 mole per liter. Okay, now what I have to do, sorry, 0.06, I'm so sorry, 0.06 it will come mole per liter. Okay, now similarly I can calculate for the H2, concentration of H2. So concentration of H2 will come something like, again 0.40 divided by 10, so it will again come up to be 0.04 mole per liter. Okay, here I am calculating for the CO2. So concentration of CO2, if I just calculate, it will again come up to be same, that is 0.04 mole per liter. Okay, so now we can calculate the K value. So here I can do it. Sorry. Here I can proceed with the K calculation. So K is equals to concentration of H2 into concentration of CO2 divided by concentration of H2O into concentration of CO. Right? So if I just put the value 0.04 into 0.04 divided by 0.06 into 0.06. Okay, so overall it will come up something like 0.44. So that is the value. I guess this is clear to you. So yeah, let's proceed further. Okay, mention 3 major application of the equilibrium constant. Okay, so here you can see first it's to predict the direction, extent to which the reaction will occur, equilibrium concentration. For this purpose we can use the equilibrium constant. Here you can see define reaction quotient. So reaction quotient means that ratio of the concentration of product by reactant at any extent. Okay, so at any extent, not in equilibrium, that's it. That is reaction quotient. It can be written in the term of concentration as well as partial pressure. Let's proceed. Here you can see how do you predict the direction of reaction of equilibrium constant and reaction quotient. So there is a relation. If you can see QC greater than KC, then the reaction will proceed in the reverse direction. Okay, means backward. If you see QC is lesser than KC, then forward direction. If they are equal, then they are in equilibrium. Okay, let's proceed. This is the condition that I just told. It's taken from the NCERT. Okay, so here one problem comes. Let's proceed with that. So they are saying a mixture 1.57 mole of N2, 1.92 mole of H2 and 8.13 mole of NH3 is introduced into a 20 liter reaction vessel at 500 Kelvin. At this temperature, the equilibrium constant Kc for the reaction is this. The reaction mixture at equilibrium. Is the reaction mixture at equilibrium? If not, what is the reaction? Okay, so first we have to find out the QC here, and we will check if QC is equals to Kc. If it is not equals to Kc, then we can tell that it is not in equilibrium. Then if it is lesser than and greater than, that we have to check, and in accordance to that we can tell that. Okay, so yeah, let's find out the QC. So QC, if you want to find out for the reaction, so definitely NH3 whole square divided by N2 into H2 cube, right? So now just put the value. So if you just put the value, that is 8.13, right? 8.13 mole. Okay, so now in 20 liter, right? So divided by 20, okay, whole square, divided by again 1.57 divided by 20 into 1.92 divided by 20. So mole per liter here, square and below also it will be getting cancelled out. So if you just find out the value, it will come up to be something like 2.38 into 10 cube. That is a QC value. So as you can see, it is not equals to KC, right? Rather you can see QC is basically greater than that of the KC, which indicates it will follow backward direction. Okay, I guess this is clear to you. Let's proceed further. Okay, say the Chatelier principle, I guess just direct question it is. If a constraint is applied to a system at equilibrium, the system itself adjusts to nullify the effect that is applied. Okay, so here you can see, if explain the effect of pressure on the equilibrium. There's CO plus 3H2, CH4 plus H2O. Okay, so here you can see, if you apply the pressure, then it will go towards that direction where there is lesser number of moles. Okay, so what I said, if you on being applied pressure, if you apply pressure, then reaction will move to a direction where there are lesser number of moles. There are lesser number of moles. Okay, so you can see, if you apply pressure, both the side I am having gaseous, but in the reactant side I am having here 1 plus 3. Reactant side I am having total 4 moles. Okay, and this side I am having total 2 moles. Okay, so if you apply pressure, it will proceed to this direction, towards product direction, lesser number of moles to minimize the pressure. Okay, I guess it's clear. So it will move towards the direction where there are lesser number of moles. So it will move towards the product side. Okay, so let's proceed further. Okay, so the equilibrium remains undistributed. Okay, next you can see the equilibrium remains undisturbed by the addition of inert gas at constant volume. Why? So the reason is basically it is because the addition of inert gas at constant volume does not change the partial pressure. Okay, why? Because whenever the gas is inert, it will not react, right? So that's the reason, it will not change the partial pressure or the molar concentration of the substance involved in the reaction, because it will not take part in the reaction if the volume is fixed, right? So that's the reason it will not disturb the equilibrium condition. Let's proceed. What is the effect of change in temperature on equilibrium? So here you can see, if I'm having, let's say, endothermic reaction. Endothermic reaction means that requires heat. So in case you are giving temperature, it will proceed in a forward direction, means it will try to utilize the temperature you are giving. But if you are doing any exothermic reaction, then if you give temperature, it will proceed backward direction. Why? Because if the forward process is exothermic, backward process is endothermic. So it will try to utilize the heat you are giving. So it will proceed backward direction. Okay, let's proceed. What is the effect of catalyst in equilibrium? There is no effect in equilibrium condition, but catalyst helps to reach the equilibrium faster. Okay, means once the equilibrium is reached, it is like attaining the forward and backward direction reaction in a same way, right, in a same rate, so there is no effect as such, same extent, right. So as a result of this, there is no as such effect. But whenever like equilibrium is not attained, that time catalyst will try to make the equilibrium to occur, to achieve the equilibrium faster rate. Okay, so let's proceed. Okay, what will be the conjugate base of the following? So for HF, definitely conjugate base means acid after releasing its H plus, right? So HF, once it releases its H plus, so F minus, H2SO4, that is HSO4 minus, HCO3 minus, one hydrogen will be released, hence CO3 2 minus. I guess it's clear.